So one of the things in chapter 14 that your textbook doesn't really go into a lot of detail about has to do with ionic compounds and these conjugate acids and bases that we were learning about earlier in the chapter. So this is just a separate standalone piece. I think it'll be really helpful to you, especially if you're going on to 1021, 1022. And it'll give you a little bit more information about why buffers work the way they do if you understand what I'm going to talk about right now. So to start out with, if I asked you, let's say if I took sodium chloride and put it in water, would it change the pH of that solution? Most of you would say, well, no. If I put an ionic compound into water, it's not necessarily introducing H plus or H3O plus or hydroxide ions, so it's not going to change the pH. But some ionic compounds actually do change the pH of a solution, and I want to kind of explain why that is. So to start out with, let's say we've got our sodium chloride solid. If I throw that into water, and that's all that means when I write that over the arrow. If I throw it into water, I'm hoping you still remember that this compound is really composed of separate ions, and it dissolves, and those ions come apart and make separate aqueous ions. So that's great that we recognize that, but let's take a look at each of these ions separate from one another. Will either one of them interact with water in a way to make more hydroxide or H3O plus, hydronium ion, in solution? So what we want to do to test whether or not they change the pH is take one of those ions at a time and see if we can react it with water. And this is just a hypothetical at this point. This doesn't necessarily happen, but what we're doing is sort of predicting what might happen and then looking at what the result is and saying, oh, we know that that reaction doesn't happen, or yeah, it does. So if sodium were to interact with water, and I want you to always be thinking of water as a combination of H plus and OH minus. So if sodium was to interact with one of those two ions, which one would it be? Hopefully you recognize we can't have it reacting with H plus to do anything. So it would likely, if it were going to do anything, be attracted to the hydroxide ion by the opposite charges. So let's just write that as one of the possible products of this reaction. So if the sodium took a hydroxide away from water, what's left over? Got an H plus left over. So that would have to be one of my other products. Now the question is, does that reaction really happen? I can write it. That doesn't mean it really occurs. If this reaction did happen, it would make a bunch of extra H plus in solution and would make the pH acidic. So that sodium ion by itself could make that solution, make the pH of the solution change. But this doesn't happen. What do we know about sodium hydroxide? What kind of base is it? Is it a strong base or a weak base? Well, it's a strong base, and if you don't know that, make sure that you go back and review the list. There are only 6 strong bases you need to know, and this is one of the important reasons for knowing that. So if it's a strong base, what does it mean that it's a strong base? Why is something a strong base? That means that if something that we consider a strong base is in water, it exists as separate ions. Those ions aren't attracted to one another. They're actually floating around separate from one another. So the fact that this is a strong base means these two ions aren't attracted to one another. The sodium won't pull a hydroxide ion away from water, and this reaction won't happen. And that's all because in our predicted products, we've formed a strong base, which we know really isn't going to happen. We can do the same thing with a chloride ion. And again, we're going to think of water as being a combination of H plus and OH minus. So chloride is going to either interact with the H plus or the OH minus. And hopefully we see we're not going to make anything with this hydroxide ion because they have the same charge and they'll repel each other. So it's possible for me to combine the H plus and the Cl minus to make HCl. And if the chloride were to have taken that H plus away from water, it would leave behind OH minus. So if this was the case, if this reaction really occurred, there would be a bunch of hydroxide left over in solution, and it would be a basic solution. But what do I know about HCl? Is it a strong acid or a weak acid? And again, it's on our strong acid list. And again, the fact that it's a strong acid means that those two ions are not attracted to one another. They have such a weak attraction that as soon as they're in the water, they fall apart and they float around independent of one another. So this doesn't form either. So since neither of those two ions interacts with water to make H plus or OH minus, it doesn't change the pH. So a solution of sodium chloride would be considered neutral. Or it has a pH of 7, just like pure water would. But let's try something where maybe one of these reactions does happen. Let's say that we have sodium cyanide, another ionic compound, and I ask you, is a solution of sodium cyanide acidic, basic, or neutral? Again, you'd say, all right, I'm going to put that into water. It's going to split apart into its separate ions. And here again is where if you don't know your polyatomic ion list, you're going to really have a lot of trouble. So we have aqueous sodium and we have cyanide ions. So now let's take a look at each of those ions separately and see how they interact with water. Well, I don't want to rewrite this whole sodium thing out again because I just erased it. It's in your notes. Sodium doesn't react with water because it would tend to form that strong base. So plus water, no reaction. And you can look back at that. But let's test that cyanide ion. And again, remember, water is composed of H plus and OH minus. The cyanide with this negative charge is going to interact with the H plus. And if it pulls H plus away from water, it's going to leave behind OH minus. Now, I look at what I'm forming here. It's an acid, but it's not one of my strong acids. It's actually a weak acid. And what does it mean when something is a weak acid? It means that those two ions are so strongly attracted to each other that not many of them come apart when I put it into solution. So what it's really saying is cyanide ions really like to be paired up with the H plus, so much so that they tear it away from a water molecule when they're put into solution. So as soon as that sodium cyanide hits the water, dissolves into these two separate ions, the sodium just floats around, doesn't do anything. The cyanide starts tearing protons away from water and forming lots of molecules of HCN. Because remember, weak acids exist mostly in the form of the molecule, not as separate ions. So most of them look like this. And as that cyanide is pulling protons away from water, it's leaving behind a whole bunch of hydroxide ions. And remember, the thing that causes a pH difference in solution is either hydroxide or the H plus floating around by itself. So when I look at this entire set of information, what I've done is I've made a whole bunch of extra OH minus, which is going to make my solution of sodium cyanide basic. So this is going to be a basic solution. And again, the fact that we make a weak acid doesn't make it an acidic solution. I'm trapping ions together so that they can't really behave very well as an acid, and I'm making a whole bunch of hydroxide ions in solution. That's what makes that solution basic. So let's try one more where maybe the other ion is the one reacting. So let's take a look at a solution of ammonium chloride. So we'll take our solid compound, throw it into water again, and ask ourselves, is that going to be an acidic, basic, or neutral solution? And remember, here's a polyatomic ion. Now, the reason I can only ask you, is it acidic, basic, or neutral, is because to actually figure out what the pH is requires a whole lot more information about equilibrium and equilibrium constants, things that you won't really learn about until 1022, and you'll spend a lot of time really working through a lot of the details of these kind of problems. But you can actually estimate whether or not it's going to be acidic, basic, or neutral and come out correct. So I've got these two ions now, and I want to treat them separate from one another. Again, draw or write out their reactions with water. So here's this ammonium ion, plus charge. Is it going to interact with H plus or OH minus? It's going to grab the OH minus and make some ammonium hydroxide. And if it pulls this hydroxide away from water, it's going to leave behind H plus ions. So I formed a base, or I've predicted that a base will form. Is it a strong base or a weak base? Okay, so it's not a strong base. It's not on our strong base list, but there's this hydroxide there. So I know it has to be a weak base. And again, the definition of a weak base or a weak acid means that those molecules tend to exist because they don't separate. Their attractions are so strong between one another that they don't really dissolve to any great extent in solution, which means that if somehow I can have this ion by itself and throw it into water, it starts pulling those hydroxide ions away from the water molecules and leaving behind a whole bunch of H plus or H3O plus, whichever way you want to think about that. So I know I've got a bunch of H plus that I've formed in solution, but I want to make sure that I don't ignore the other ion, the chloride. And I'm not going to write this whole thing out either because it was in the first example that we did. And we know that it's going to form HCl, which is a strong acid. So this is not going to form any compounds, any products, so we have no reaction there. So the only thing that's going to interact with water out of this ammonium chloride is the ammonium ion, and it's going to react, form some weak base, and make a whole bunch of H plus in solution, which would make this an acidic solution. So an ammonium chloride solution is acidic. So that's something to think about. There aren't many practice problems there. There are some on old exams that I've posted. I'll try and maybe post a worksheet or something that you can work on that has a few problems of this type. But really, this is more to help you understand how buffers work and really why they work the way they do, on top of just understanding what a conjugate acid-base pair is. So give some of those a try and make sure you drop by if you have questions.